all the sort of untapped data that's available. If you can imagine a system which was actually able to just learn, for instance, from watching videos on the internet and stuff like that, rather than being reliant on that kind of parallel corpora. It's also maybe closer, I think, conceptually to like how we actually learn language. So now that I'm selling his research agenda is better than my own, I will stop and let him actually present.
Okay, well, thank you so much, Jonathan, for that great introduction. Thank you to all of you for joining me here today. I'm really, really excited to be here at CMU. I've actually never even been to Pittsburgh before. This is the first time I have been on an airplane in about 2 years. So I'm really excited and happy that I was able to come see you today. So my talk is going to be about learning representations of speech with multimodal self-supervision. So the key idea here is really going to be multimodal self-supervision. We're all very familiar with self-supervision, but I'm going to hopefully try and convince you today that maybe there's more than one way to think about self-supervision, and that maybe there are some interesting synergies that can happen when we look at multiple forms of self-supervision together. So, oh boy, come on. Okay, well, that's all right. So the first thing that I'm just gonna say is, and this is how many speech talks start nowadays, is talking about how amazingly successful our field has been recently in developing speech recognition technology that we've actually been able to bring to market and be very, very profitable. So if you think back to like my favorite example is like HAL from 2001: A Space Odyssey. Gosh, 50 years ago now, where, the fact that, Dave could talk to Hal was like a science fiction pipe dream, right? And this idea that we could be talking to our computers was something that seemed so far out of reach back then. And yet, after many decades of really hard work by many thousands of different researchers across the world, today we actually have technology which works pretty well. Obviously, the problem isn't completely solved, but our technology is at a state where in a lot of cases, it's useful enough to be used by many millions of people around the world. The learning paradigm that actually powers all of that technology that you see in products like Siri or Google Voice Search, though, is actually based upon this paradigm, which is about 40 years old now. And it's this notion that, it all kind of comes back to this sequence to sequence learning problem where you have where you've got basically a speech waveform that you record, and then there is some kind of ground truth transcription that a human being has provided to you in the form of like words or word pieces or characters, basically just a transcription or an account of what was said in this particular utterance, or like this, chopped up like sentence of speech. And basically all of our learning algorithms, whether you're looking at like modern day neural networks or hidden Markov models from the classical approaches, they kind of treat learning as this like, predict the bead sequence on the string given the waveform, right? And where each bead represents, a word or a character or a subword unit or so on. And this is not at all how humans learn speech, right? Each and every one of us learned to communicate with spoken language. We acquired language from raw speech audio entering our ears without any kind of, oracle knowledge of like, the words being spoken or the orthographic representations. So I think the ability to imbue computers and computational models with that same kind of that same kind of capability is really going to be a game changer in order to actually, extend ASR technology and spoken language understanding technology to all the people and all the languages all throughout the world, right? So there's, I think to date, the languages that are still spoken on this planet number around 7,000. I think, there's, I think half of them are spoken by like less than 10,000 people. And so there's this enormous long tail of languages that we want to have modeling capability for, but it's just really, really, really difficult to follow this kind of standard supervised learning formula that we have that we know works on really high resource languages. And it just doesn't seem like it's going to be able to scale to handle everything. And I would really argue that this, for a long, long time, probably still today, has really been just a fundamental challenge for all of AI, whether you're talking about speech recognition or something else. Many successful machine learning tasks in practice rely on having large quantities of annotated training data, where you've basically got some kind of input signal and then some sort of output label, and you train the model to basically predict like the output from the input. And usually these outputs are going to be things like class labels or transcriptions that have to actually be specified in advance and handcrafted by human beings. It's incredibly labor intensive, and it doesn't really scale. So the other problem is that once you've actually crafted that set of classes, for example, it's like, well, how are you going to deal with the situation when you want to learn something new, right? Well, you have to go collect more data and have humans annotate it, and that just doesn't really work for us. And so, there's far more raw data in the world than there is annotated data. And so the question is, can we use it somehow? Can we build models that learn with much less of this handcrafted supervision by leveraging this sort of unannotated data? And over the past few years, we've seen this amazing trend that has, taken hold in the NLP community, in the vision community, in the speech community, where we use so-called self-supervised models that learn on large amounts of unannotated data, and then you can basically go and fine tune them on your task of choice, some downstream like task specific data set where maybe you don't have a ton of labeled data, but you can still do pretty well. And the idea is that kind of by doing this pretext like self-supervision task, the model has kind of learned the lay of the land such that it doesn't need as much annotated training data to reach a certain level of performance on the downstream tasks. So to give you an example of what that looks like in speech, this is Wave2Vec 2.0, one of several extraordinarily popular models now that we have in the speech community, where the idea is that we're going to basically take 1 to 60,000 or more hours of just like audio data that's untranscribed, just recordings of people talking, basically do an analog of the masked language modeling objective that's used for BERT to train this model. And then we're going to go and fine tune this model to do something like automatic speech recognition on a relatively small amount of transcribed data. And so to give you an idea of how well this actually works in practice, these are some examples from the Wave2Vec 2.0 paper, where comparing against contemporary models which are fully supervised, underwent fully supervised training on nearly 1,000 hours of transcribed speech, hitting word error rates, in depending upon whether you're looking at clean or noisy data, around 2 to 5%. Wave2Vec 2.0, which was underwent self-supervised training on the 960 hours, but then only had 1 hour. So like 0.1% as much data to train on in supervised fine tuning, was able to achieve, error rates that are sort of comparable. Maybe they're a little bit higher, 3 to 6, 7, 8%, et cetera. But, these would be way, 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 way higher if you just train the model from scratch on only 1 hour of transcribed data. So the talk what I'm going to be talking about today is, I think it's still in the realm of self-supervised learning, but it's really posing the question about, well, are there other forms of self-supervised learning that maybe we should be looking at, right? In addition to maybe just like unimodal masked prediction of the input signal. And actually, there's this really cool paper that goes all the way back to 1994 from Virginia Dessau, which is, as far as I know, I could be wrong, but I think this is the first time I've ever seen self-supervised as the phrase appear in a paper. And actually, what she, the way that she defined it is that here she's talking about sort of image classification, where you have some image, maybe it's a cow, and then these output neurons in your neural network, basically you're trying to predict like a one-hot output where, the dimension you're trying to have be 1 corresponds to like the cow label. And she's arguing that this is sort of like implausible from like the standpoint of humans, because we don't have like an oracle that's like kind of pulling up like one neuron in your brain saying, no, this is the thing that needs to fire. She contrasts that with like unsupervised learning, which has limited power because all you can really do is maybe like some sort of like density estimation, and you can't really link it to some sort of like symbolic label. And then self-supervised learning, the way she formulated it, is where you actually have two different inputs, which are coming from two different modalities, and they share the same underlying label. So in this case, it could be like the cow and then the sound moo, for example. And the idea being that, well, if you extract representations from both of these, and then you essentially learn to match the outputs together, that you could kind of have, this image classification network like derive its label from the audio classification network and vice versa. And so this is the main idea behind, this particular formulation of self-supervised learning. And, to hopefully convince you that maybe this isn't something that's, totally implausible, and maybe there is, some sort of motivation into why we should be looking at this as a learning objective. I'm gonna play a little video here, which should hopefully resurrect, some early childhood memories in all of you.
In the summer, I like to lie in the sun and watch the birds. And I like to watch the frogs in the pond. Then I curl up in my hollow tree and dream about spring. The end.
So I won't play the rest of the video because it's just more crying. I have two young children at home, so I hear enough of that. But just like our machine learning models that we have nowadays, I think it's also the case that human beings, they also get angry when you stop giving them training data when they're trying to learn. So what I want to talk to you about, and this is basically what we're going to be doing, this is kind of like the central message of the rest of the talk, is we're going to be thinking about using cross-modal grounding as a learning objective for these models. And so the big idea is that if you've got some intelligent agent, which is trying to learn both perception of speech audio and maybe visual perception at the same time, what we're going to do is we're going to present it with inputs which are somehow correlated, or they're somehow matching the same way that Virginia Dessau outlined in her 1994 paper. And so what we're gonna assume is that we've got some visual images, and then we've actually got spoken descriptions that are talking about the content of the images. So we essentially have people describing that, oh, I see some lambs standing on a green grassy field, et cetera. And the idea here is that if we can actually get this model to learn how to associate these inputs together, then implicitly it should have learned to do at least three things. Number one, it should have learned to recognize some of the words in the speech signal, hopefully a lot of them, which is a non-trivial problem. I mean, that's why ASR exists as a field, because if I told you to tell me where the word boundaries are in this waveform, I don't think any of us would be able to do it. Or even to identify like what the words are, just by looking at the waveform. It's not self-evident. It must have also learned to recognize objects, visual objects in the image. And then finally, it has to have learned how to ground those two different abstractions together. And so it needs to know how the words in the speech waveform relate to the objects in the image here. So this is the outline of the rest of the talk for today. I'm actually going to talk about 4 different research projects that are, that all kind of sit underneath this learning task umbrella, so to speak, that I just introduced. And they're going to be a little bit chronological. So I'm actually going to start by talking about work that is a couple of years old now, but it actually serves as kind of the foundation for a lot of the other stuff that we've done here. And there's some really, really cool demos that I like to play too. So let's start by just looking at how we would actually learn representations of speech with visual grounding. So when we first started looking at this particular task, we didn't actually have a data set to work with. So we had to actually collect our own data set of spoken captions. So we did that by taking the MIT Places data set for image classification, putting it on Mechanical Turk, and basically giving people an open mic to just describe what they see. And when we do that, I'm going to give you a little demo of sort of what that language sounds like.
There is a small child wearing pink sunglasses in a playground.
So we collected to date, I think close to 1 million of these spoken descriptions for several different data sets. Like we have read versions of all the MS Coco captions. We have all these freeform ones for places. We've collected English, Hindi, Japanese data. I'm not going to have time to get into all of that, but I'm just going to, sort of roughly talk now about like the type of models that we've been using to actually like solve this cross-modal grounding problem between speech and images. So the models that we started looking at back in like 2016 were based upon these dual encoding convolutional neural networks, where basically, you take something kind of like a BGG architecture, because that was the state of the art at the time. You encode the image down to some, 14 by 14 grid of 1024 dimensional embedding vectors, and you do something similar with 1D convolutions operating on the speech signal. So the idea is that the dimension here is the same, right? It doesn't have to be 1024. In this case, it is, but because I have this shared dimension between the speech representations at each temporal frame and each spatial location in the image, then I can take something like a cosine similarity or a dot product, et cetera, and I can form this affinity tensor, which we call a match map. And then the idea is that like where you have large similarity is going to be colored red here, and then white where you have low similarity. And so if somebody said the word girl over here in the speech, what I'd like is for this alignment tensor to then tell me that, okay, well, this is where the girl is in the image. But the issue is that we don't actually have like ground truth alignments that we can use to train with to regress to. So instead, we're going to have to come up with something that's a little bit more clever in order to get these things to emerge naturally. So what we do is we actually just define a function which takes one of these as input and outputs like an overall scalar valued similarity metric between like the image and the caption. And then we're going to train the model to associate images and the captions that actually describe them together using a contrastive loss function. So this could be something like the triplet loss or info NCE. They all work pretty well, but intuitively they're kind of the same. You basically take the representation that's output by your model for the image and output by the model for the speech, and you try to make them similar to one another according to whatever similarity metric you defined. And then you go elsewhere in your data, in your big bag of data, you pull out some random waveform that doesn't describe this image because we collected it for some other random image in the data. And we say, okay, well, the model's similarity score between these two inputs should be as low as possible. And then you can, of course, make this symmetric by considering like images as imposters and then holding like, a speech waveform as the anchor example. So this is basically then how we get these models to learn. And the very first thing that we then did is look at, because this is more or less an information retrieval type task that we're using as the pretext task. Let's just see how well the model actually performs at this task and how well it learns to essentially, do this sort of like semantic Google image search based image retrieval where you have these queries which are in the form of speech waveforms. And, so we're really just doing this end to end. You could imagine building a model which first uses like ASR and then, transcribes the speech into text and then does some sort of text image matching, but that's not what we're doing. This is all end to end. There's no notion of words or transcription. We're just trying to directly learn the semantics from the speech signal. So we're going to evaluate this just with standard information retrieval metrics, such as we're going to be mainly looking at like recall at the top K examples here on some held out validation set. And so random chance on this particular task is going to be 1% because we're looking at recall at the top 10 hits over 1,000 examples. And if we're doing pretty bad if we just kind of try to do this randomly, right? But immediately our model just sort of like right off the shelf with no other kind of, pre-training or anything like that is achieving, 45 to 50% recall at 10. So it's working pretty well right off the bat. And if we look at ways of doing some sort of either supervised or unsupervised pre-training by like taking image net weights, or again, we just did this unsupervised pre-training on a very, very large amount of video data from the Flickr SoundNet database. They both work about the same, and the retrieval scores are here now pushing like 70%. And actually, if you just then replace the speech with instead like word embeddings and build a model to process those instead of the speech, so it's sort of like a text to image matching model. Now we're getting 5 to 10% better. So it is still better to have the words, at least for this model, but it's not a whole lot better. And I'll actually show at the end that we've more or less completely bridged the gap between these end-to-end speech models and text image matching models when the input is spoken and when you have access to high quality ASR. But to convince you now that these models are actually learning some sort of reasonable alignment tensor between the speech and the image without us actually having to provide some sort of handcrafted annotation, I'm going to play this little animation where we basically took a snapshot for this input at every single epoch during training. And you can see that things kind of start off really diffuse before they converge to these blobs, which actually seem to represent some kind of alignment between the speech signal and the image. But because I can't really read that spectrogram, when it's like all the way down there like that, I think a much more effective way of visualizing this is I'm gonna overlay this as an alpha mask over the image, and I'm gonna play it back synchronously with the audio of this speech here. So you can actually see what the model is associating the speech with at each point in time. And so it's gonna look a little bit like this.
This is a photo of a girl standing in front of a lighthouse. The little girl is wearing a blue print dress. She has blonde hair and blue eyes. The lighthouse in the background is white with a red roof.
I have a real-time demo of this working on my laptop, and if there's time at the end, anybody who wants to can come down and play with it on the laptop. But I'll just play another couple of examples.
Here we see a stretch of grass and a small road leading up to a very old ancient ruin.
A white and blue jet airliner near trees at the base of a low mountain.
So one thing that you may have noticed that I did there is that I did some thresholding of the attention map and then essentially extracted like connected components from it in a volumetric sense, and then I color coded them. And that was basically to derive like a semantic co-segmentation, right? Because we can kind of extract like a region of the speech, which hopefully covers a word like girl, as well as a region of the image, which hopefully covers the girl. And so once we do that, we can basically use these masks to pool the embedded representations learned by the model, and then do something like clustering on top of those across our whole data set, and we can actually learn a picture dictionary. So here what I'm showing you is like the 9 most central image crops for each cluster, and I'm going to play the 3 most central speech waveforms that are assigned to this same bimodal cluster.
Castle.
The castle had
castle
on the couch, round couch.
and a couch.
Sunset.
the sunset,
Sunset.
The train.
Train.
the train,
Wooden.
The lighthouse.
A lighthouse.
A lighthouse.
So hopefully this has convinced you that maybe the model is actually learning like to recognize words and objects and how to link them together at the same time. I won't play you all of the clusters that we found because there were actually several hundred of them that were learned by this model. So I'm just going to instead show you the majority vote of like the underlying transcription of the speech segments that were assigned to each cluster here. And as you can see, it's mostly learning things like objects or backgrounds or textures, in some cases colors, stone, it shows up here. I think there's also like, I don't know if wooden is in here. No, these are all just objects. Well, baseball is kind of an abstract concept that learns to associate it with baseball players. But like I said, there's on the order of hundreds of different concepts that are being learned by these models. So now I'm going to shift gears a little bit, and I'm going to talk about some more interesting things that we can actually do with these models, after we've kind of demonstrated their capabilities. So the first one is something that we did a couple years back, which I think now is becoming more and more popular in our community, which is this notion of automatically discovering discrete representations of speech. So it's like we want to kind of automatically learn these units from the speech signal, which correlate with maybe phones or with words. And the motivation there is that if we were able to do this, maybe we could actually start doing like very rich, like spoken language understanding or NLP directly on the speech signal. And I think that this is a well-motivated thing to do because all known human languages convey their meaning with discrete words, which are composed of a finite set of sounds, phonetic units. And usually languages only have like a couple dozen of these phonetic units. So it seems hopefully reasonable that maybe we can learn them in this data-driven fashion. I mean, at least for the language that we've actually got the data for. The other thing is that there's many advantages to having, discrete representations of speech rather than things that are continuous. Discrete representations are more likely to be interpretable. They're more likely to enable us to apply models in a modular way. Maybe we can even adapt these models to do something kind of like speech transcription for languages that don't have a writing system, or at least enables us to do NLP on speech from languages without a stable orthography or a writing system. Maybe it facilitates few-shot learning because you can learn how to compose the subword units that you learn into like new vocabulary words, and so on and so forth. So this is a slightly updated model because this is a couple years later after the initial work we did, which is now all based on ResNets. But basically the idea here is that, there's still this kind of semantic supervision that's coming from this cross-modal matching task. And actually a lot of the work that, several people working in this area had done in sort of the years leading up to this work, and the things that people are still working on, is actually like analyzing the representations learned at different parts of these models. So one of the consistent findings that a lot of papers have found is that at the lower layers of these models, the representations tend to be correlated with very low-level speech units, such as phones. Whereas at the higher layers here, they tend to be correlated with larger units, such as words. And so what we're going to actually try to do is, instead of just learning these representations and then going back and doing some sort of post hoc analysis to see what they're learning, we're actually going to see if we can get the model to automatically learn these kinds of discrete representations during this multimodal training. So the technique that we're going to use to do this is actually borrowed from the VQ-VAE model, where what we're going to do is we're going to basically insert like a discrete bottleneck at strategic locations within this network. So what you would normally have between these two different residual blocks is this just continuous representation X, right? That feeds from the output of like res block 2 to the input of res block 3. And so what we're going to do instead is we're going to posit that there is a finite sized codebook of vectors. So here there's like 3 of them, E1, E2, and E3. And what I'm going to do is I'm going to first, as X comes out of res 2, I'm going to basically compute the Euclidean distance between X and every single one of the codebook vectors. And then when I go to feed the representation into res 3, I'm going to replace X with whatever codebook vector was closest to X. So in this way, we're basically forcing a discrete bottleneck here where there's only like one of k different values that this embedding is allowed to take on. And so therefore, the third residual block is only ever to take like, these discrete units as representations. And this is all trained with some tricks, like using straight through estimation to handle the fact that this breaks SGD. And we actually, instead of like updating the code books, with the gradient, we instead do some sort of like exponential moving average on the points that were assigned to them, so on and so forth. All of that isn't super important. The main thing is that we can basically just learn all of this end to end. And the other cool thing is that we don't have to limit ourselves to just using one of these discretizers. We can actually insert however many we want. And given that we hypothesize that the lower layers of the network should capture something like subword units, and maybe the higher layers should capture word-like units, let's try going and adding some quantizers in the bottom half and then in the top half of the network. So when we do this, it's really cool because we again, confirm that the lower VQ layers do indeed capture, discrete units that seem to be correlated with phones. So here I'm just plotting this density where each element in this big matrix is basically giving you the conditional probability of a particular phone label given the unit label. So you basically look at all of the times that like this unit was active on your data, and then you go and see and look at what the actual phone was at that point in time. And then we basically diagonalize this matrix, and we see that we have this kind of emergent grouping according to like manner classes where you have like nasals and stops, alveolar fricatives over here, vowels and approximants over there, etc. So it does seem like these lower layers are actually learning something correlated with English phones. We can actually quantify this a little bit more robustly by using this ABX metric, which we borrow from the Zero Speech Challenge, where basically the task is given A and B, which are phonetic minimal pairs. So this would be like bug and this would be bag. X is either going to be bug or bag. And the idea is that based upon the representations computed by the model, we want the model to say that X is more similar to A or B, where, whichever one it actually is like, shares the same underlying word identity, right? So there's like two different instances of bugs spoken by two different people. And we want the model to say that A is more similar, X is more similar to A than X is to B. And so the way we're going to do this, we're going to extract those discrete codes with our model. We're going to also pull along the representations that were learned for each of those. And then we're going to compute these distances using something just like dynamic time warping. And then we're going to multiply those by -1 to get the similarity. And then that's the ABX task. So you're correct if f of x is closer to f of A than to f of B. So random chance here is just 50% because it's just a binary guess, and lower is better. So comparing our model, the VQ2, yep. That's right. So you just copy, you just compute the gradient of the loss with respect to E1, and then you just copy that over to X, and then you push it all the way through. Yeah, and then like E1 gets updated by looking at, within like a batch, all of the vectors that were assigned to E1, and then you just take like a convex combination of like what E1 used to be with the average of all of those vectors. Okay, so looking at the Zero Speech 2019 English test set, the best performing model on this metric at the time was this WaveNet VQ based paper, which was achieving 19.98% ABX error rate. And actually, when we take that model and we just train it on our audio data, because there's a specific training set for this task, which is different from the Places audio captions, which we used. We see that actually it gets worse because there is some domain mismatch between our training audio and the training audio from the task. But when we use our model, which again was trained on the same data as this model here, we see that we're doing much, much better for the ABX task, on the order of like 12 to 13%. But what's really interesting here is when we look at what happens with this layer here, what's going on? Because this is much, much, much worse than the representations learned by the models here. And so what we think is going on here is that maybe this is not this VQ3 layer is not learning something correlated with subword units, but instead it's actually capturing word identity. And we confirm that this is the case by basically looking at this metric we define, where we treat every single one of the codes as a potential word detector. So you can basically you can look at all the times that a particular code was predicted on some test data, and then you can compute what the F1 score would have been for that particular codebook entry and every single potential word. So you consider like, okay, if code 17 was a detector for cat, well, let's look and compute what the F1 score would be for that code and cat. Now let's look and see what the F1 score would be if we treated it as a detector for dog. And then what we basically do is we sort those F1 scores for every code, and we look to see if there was some word which achieved an F1 score of greater than 0.5. And we call any codebook entry which achieves that a word detector. And so in this case, we're finding that this model where VQ3 failed to learn good phonetic representations, it actually learned several hundred different codebook entries that were very effective word detectors. And most of the words that were learned by these detectors are, again, sort of the same kind of visual words which we were learning before when we just applied this post hoc clustering. So there are things like baseball or classroom or construction, playground, kitchen, so on and so forth. And we can actually also look at the unit alignment between the VQ layers here and the underlying forced aligned transcription of the speech. So it's really cool. Like in here, you've got two different utterances where the word train has been spoken. And you can see that like unit number 248 from the VQ3 layer is pretty well aligned to both spoken instances of the word train. And then I highlighted in green, this is the VQ2 layer underneath that. the shared subsequence of these smaller tokens between this instance of train and that instance of train there. So for example, it seems like unit, if you really kind of squint, like unit sequence 358, 306 is present in both, and it's kind of happening right around the TR at the onset of the word train in both cases. And as an extra bonus, adding this discrete inductive bias to the model actually also helps the retrieval performance on that original retrieval task. So now I want to move on to the next topic, where we're actually going to be looking at learning to now generate spoken image descriptions for an arbitrary image without using text. So here, what we're going to do is, given this image down here, we actually want to generate an audio waveform which describes what's going on here, and we want to do it without having to use either a text captioning model or a traditional text-to-speech system. And so again, the motivation here is, well, humans can learn to do this before they ever learn to read or write, so why can't computers? It's also, intellectually interesting because most of the text-free speech studies up to this point had really only focused on looking at like inference tasks and what the representations were capturing, but not many people at the time had really looked at generation of speech. And the other cool thing is that image to text has also been studied extensively as text captioning. So that provides a whole bunch of reusable metrics that we can use to evaluate our system. So the approach that we're going to take is actually to use these discovered units from the model I just presented as like a drop-in replacement for text data. So again, the motivation here is that even for languages that don't have a commonly used writing system, there are still inventories of words and phonemes. So it probably makes sense to, again, be looking at discrete units to represent the speech. Another benefit of using this pipeline system, where here we're going to have this captioning model, which I'm going to call an image to unit model. And here I'm going to have a synthesis model, which I'm going to call a unit to speech model. Again, I'm using unit in place of text here because we're using these discrete units inferred by the model rather than text, is that we can separate the training of these two different modules, and we don't have to do the end-to-end training, which we found to be much more difficult. So the detailed model diagram for how this works, it looks complicated, but it's really not, because this is just our ResDaveNet VQ model that I talked about in the previous slides, which is basically acting as a, sort of like an unsupervised speech recognition module, where we're taking in an input spectrogram and just transcribing it into a series of these discrete speech units. And then the idea is on the image side, we're basically going to take a data set where we have images paired with spoken captions. We're going to infer what all these codes are for every single one of the spoken captions. And then we're just going to take a standard off-the-shelf image captioning model and learn to generate those code sequences as if they were text. And then once we are able to generate a sequence of these learned units, given an input image, we're going to separately train this model here. We're just using Topotron 2 to synthesize the speech waveform that would go along with a particular unit sequence. Again, to do this, all we have to do is just take the training data we would have normally used, paired text and speech. We're just going to throw away the text, transcribe the speech into the units, and then train the model to reconstruct the speech given the units. One of the big questions that we looked at here is whether different units or encodings of the speech are equally suitable. So we actually compared the units coming from different VQ layers of our model, as well as, again, the WaveNet VQ model, which was trained with a reconstruction task rather than this grounding task. And we also looked at whether we can use units that are happening at a fixed, like, uniform frame rate versus ones that actually have a variable frame rate, which we're going to derive with run length encoding. And so what we found is that when we do the beam search decoding on the first half of the model, which is trying to predict a sequence of units given an input image, the only case in which we're able to do that reliably is when we use this run length encoding. So basically, when you have these uniform frame rate units, essentially the decoder kind of gets stuck in these infinite loops because it tends to see lots of like silence units happening at the beginning of an utterance. And so you just don't want it to get, because it doesn't have enough, sort of like memory in its modeling capability to like know when to stop outputting silence. We found that basically without RLE, everything just kind of fails. And we also actually found that that was the case for the WaveNet VQ model, even when we applied run length encoding to it. And so to give you some quantitative results here, which is the way that I'm deriving these is actually now after the fact, we simply just take the synthesized speech that our model output and we run ASR on it to transcribe it into words. And so it's going to be noisy, but at least now we can actually go and turn towards like blue, meteor, rouge, splice metrics because we have the ground truth caption text for each one of the images. And so we can just compare that text to the text that was generated when we run ASR on a generated speech. And we can see that, generally we are achieving pretty good scores here. So like, for example, on Blue 4, we're achieving, like 0.186. Whereas if you actually just train this on a, if you just train this on a, like a ground truth, character or word representation of the captions, you're still doing much better. So we haven't solved the problem yet, but we are, doing, I think, decently well on this task. And to hopefully convince you of that further, I have some audio examples here that I'm just gonna play for you really quick. So they're just gonna go left to right.
A small airplane sitting on the grass. The man riding skis down the smelly slope. A plastic tray with fruits sitting on top.
Okay, so now I'm going to move on to the last section of my talk. Oh, yep. Oh, this is right. So none of that work used transformers. That was all ConvNets and recurrent networks. What I'm going to talk about now is where we brought transformers into the picture. Yep. Yes.
Right, and then you talk about the deferral. So I am thinking whether the other way, like use some BP or somewhere to say efficiently duplicating information, still kind of private information is maybe I could try that to the well, do you have some kind of direction?
Yes. So I think that that's exactly right. That when we're doing this run length encoding, we're essentially completely throwing away duration information, and we're relying on the synthesizer to relearn that information. Where the implicit assumption is that, well, if we have different units representing different phones, and different phones tend to have different durations intrinsically, then the model should be able to learn it that way. But we are going to have like super limited control over things like prosody. For example, because we can't like modify the duration of particular sounds. So I definitely think that we could change our approach to do that. And some of the approaches that I would probably look at first are like all the things that like the meta group has been looking at, where they're basically doing like textless, TTS without the T, right? Using like the Hubert learned units. And I know that in their work, they actually are also borrowing these run length encoding ideas, but then they're putting the duration information back on as like an extra feature. And so I think we could do the exact kind of thing. That's a good question. We're actually not. So there's no additional language model over units. It's actually just simply, whatever implicit language model is learned by the recurrent, structure of the image to unit. Yes.
They have a very strong unit language improve the performance.
No, absolutely. That's a really good idea, because then you could actually like basically have a more powerful language model for doing the generation of the units, where you can train it on just like unassociated speech data. Like you don't need to train it only on data where you have like an image paired with a spoken description. Yeah, that's exactly right. That's a really great idea. Okay. Oh, I see there's one quick question in the chat. Somebody had asked, the clusters for wooden are structures from under roofs, I think. How transfers transferable is this going to be to other data and other examples of wood in the world? That's a good question. I think the way that I would have to answer that is to maybe look at something like ObjectNet, for example, and see how well our model is actually able to, to like ground to those things. So ObjectNet, for those of you who don't know, is like a test set that's designed to like go along with ImageNet trained models, where the idea is objects are put in like very weird situations that they wouldn't normally be in. And so it's like, I could take this bottle and like put it on my head. And the idea is that the model should still learn to predict that it's a bottle, because if it's going to do that properly, then it shouldn't just be like overly reliant on the surrounding like context, because bottles are typically placed on tables. So I think I'd probably need to look at a different data set to see how well that generalizes. Okay, so the last thing that I'm going to talk about today is now moving into transformer land. So recently, transformers have also kind of taken the vision and language world by storm, and there's a whole bunch of these models which are essentially using self-attention applied to like tokens derived from multiple modalities at the same time. So these are really, really cool because they essentially allow like the visual features to attend to the text and vice versa. And this is a dramatic departure from everything that I've been showing before, because before we were always working with these dual encoder models, which basically just say, okay, there's an independent processing branch for the visual modality, an independent processing branch for the speech modality. We get some representation, and then we do all of our scoring in this space. I mean, these models have their pros because they're simple, lightweight, modular, and really, really fast if you're interested in actually using them for a retrieval task, because you can like pre-compute all the embeddings independently and then use like locality sensitive hashing to do like really efficient retrieval. But they don't have this ability to leverage like cross-modal self-attention. So this inherently should make them less powerful than these models here that use cross-attention within a shared encoder. However, these models, when you're, let's say, considering a retrieval task, they're going to be more expensive to train, and also you can't pre-compute embeddings because the retrieval is slower. So if I'm like searching a database of images given a speech utterance, right, instead of just like pre-computing all the representations in my database and then like using locality sensitive hashing to find like the nearest neighbors given the encoded speech, I'm actually going to have to do like a forward pass through every single item that I want to potentially retrieve. So this is going to make retrieval really expensive. So what we looked into, this work actually just kind of goes back to the retrieval task and says like, how well can we make these models work just for retrieval without having to, again, use speech recognition. So we built these models, which we called fast, slow transformers for visually grounded speech, or fast VGS. And the reason why we call them fast, slow is because they've really got two different capabilities that are unified into the same model. We start off with a dual encoder, but then we feed these representations into a cross-modal attentional encoder, and we get basically an output tapped from before the cross-attention, which we call the coarse similarity, and then a fine-grained similarity, which comes from after the cross-modal attention. And inside, this is basically what it looks like. In this case, we are actually using a RCNN object detector, although we've replaced it with like a self-supervised VIT, and it still works just as well. And then basically there's a transformer stack that's just processing these ROIs coming out from the faster RCNN. Down here, we've basically just got more or less WaveDivec 2.0 followed by convolutional downsampler followed by another transformer. And then we pass it into this cross-attentional stack of several different layers here, finally followed by a little MLP, which is just predicting a scalar value. So we're basically just like taking the dot product of these CLS tokens right here that are output by these transformers to get the coarse similarity. And then this MLP is processing the pooled outputs from this layer, this layer stack in order to get the fine-grained similarity. So training is again going to follow the same pattern that we looked at before, where if we have this audio here, which let's say describes our favorite image of the girl at the lighthouse, and it does not describe this image of the dog, so this is matched, this is unmatched, then we're going to input these into our model. And in the matched case, we're going to try and output simultaneously a big coarse score and a big fine score. And when we have mismatched inputs, we're going to try and minimize both the coarse and the fine scores. So during retrieval time, we can again use the model in either of these two modes. where you only just kind of chop off the cross-modal encoder and say, well, I only care about doing this fast coarse retrieval with dual encoders. Or you can use the full-fledged model with the cross-modal attention and use the fine-grained scores to do your ranking. But actually, there's something even better that we can do, which is this two-pass strategy, which we call coarse define, where if you have like a really large data set that you want to search over, you can just pre-compute all of the coarse image embeddings, and then you can do coarse search to find just like the top K candidates, where maybe K is equal to like 100, and then you just re-rank within that small list of 100 using the fine scores. And so that's how the coarse define is going to work. When we actually look at the retrieval methods, we see that indeed define does outperform coarse by a reasonable margin. Like we're looking at just recall at the top 1%. I'm sorry, one result here. So we're looking at a gap of like 38 to 42. We go to coarse define. But when we use the actual CTF scoring, we actually get the exact same performance that we would get had we run the full-fledged fine-grained retrieval over the entire data set. But what's really cool is if you then look at the retrieval time amortized across queries, we see that we're actually several orders of magnitude faster when we do coarse or coarse define than doing the full-fledged fine scoring. And so we basically get the best of both worlds with the coarse define approach, hybridizing dual encoders and cross-modal attention encoders into this unified model. So the last thing that I want to talk about now is how we can actually extend this model to just sort of learning like general purpose speech representations, which we're going to evaluate on some of the popular benchmarks, which are currently being worked on by people like Shinji right here at CMU. So this is a model that's called FastVGS Plus, and the reason why we call it plus is because we basically just add a Wave2Vec 2.0 style mass language modeling loss term here. So we add a couple of extra transformer layers. We apply masking here now, and then the idea is that with these representations here, we should also now predict the masked regions of the input. And so training is now going to be a sum of the visually grounded loss terms as well as the mass language modeling loss terms. So when we find, when we do speech to image retrieval with this model, which has been trained now with 2 different self-supervised objectives, we find that actually we do a little bit worse, surprisingly, but not that much worse, like 0.25 worse in terms of recall at 10 when we use the mass language modeling augmented model, but we're doing way, way better than we did before with our residual convolutional networks. And actually, at the time we wrote this paper, this DIME method was like the state of the art for doing text to image matching on the MS COCO data set, which is, we're working with spoken COCO, which is basically MS COCO, but with spoken descriptions rather than text-based. And we see that when you have the ground truth text, DIME is still a couple percentage points better than FastVGS. But actually, if instead you just take the spoken descriptions, run them through Google's text-to-speech engine, speech-to-text engine, and then pass those into the DIME model, it's really almost a wash between FastVGS, the end-to-end model that doesn't do any kind of speech recognition, versus the model here that has access to basically state-of-the-art ASR technology. So we more or less kind of, at least in the context of this task, bridge the gap between text-based approaches and end-to-end approaches that don't rely on text at all. So I mentioned that I was also going to show you how we evaluated the representations learned by this model on a bunch of benchmarks for various speech tasks. And we're actually doing that on the SUPERB benchmark here, which stands for Speech Processing Universal Performance Benchmark. There's 10 different tasks that are part of this evaluation. And essentially the idea is that you pre-train some large model and then you learn a whole bunch of lightweight prediction heads that are going to try and do things like speaker identification, speech recognition, intent classification, emotion recognition, etc. And we want to really learn models that are going to learn representations that are good at all of these tasks. Even when you only have access to sort of like lightweight models that you can do like the fine tuning on and maybe limited amounts of data to actually train those models. So our models are actually sitting sort of right around here in terms of their overall metrics. They're not doing quite as well as some of the very, very large models that are coming out of industry like WaveLM or Hubert, but they actually are outperforming some of those models like Hubert and Wave2Vec 2.0 on some of the tasks like keyword spotting or intent classification. And what's really, really cool here is that we're second in keyword spotting only to WaveLM, which is trained on 94,000 hours of audio data, whereas we're only training on 1.7 thousand total hours of audio, but we also have this visual context to help us. And we're almost matching them when it comes to intent classification as well. Interestingly, our model also performs decently on ASR. So it's sub 10%, but it's not doing as well as WaveLM, Hubert, or WaveTibet 2.0. But we are doing much, much worse than a lot of the other models on speaker identification. So we kind of take that to suggest that our model really is kind of maybe learning representations which are invariant to speaker identity, because that really doesn't tend to be important for this visually grounding task. So what I've shown you today is that if we just consider this idea of self-supervised learning with a cross-modal grounding objective, where we're trying to associate spoken descriptions with images, there's a lot we can do. We can learn these grounding patterns that reveal the cross-modal semantics. We can build models to do multimedia retrieval from speech without having to rely on speech recognition. We see that we get like visual object and spoken word detectors kind of emerging for free from these models. We're able to generate spoken descriptions of novel images without having to use text captioning, or text-to-speech models. And finally, the representations learned by these models actually appear to be pretty useful for a multitude of downstream tasks that we care about in the speech community. So the very last slide that I have here before I finish up is to just talk a little bit about some of the follow-up work we have that's currently in progress. One of the super cool things that one of my students recently discovered is if you actually look at the self-attention maps produced by these transformer-based models, they learn these segments which seem to correlate with word identity, and they actually seem to also segment the words. So you can see like blue, in these cases here, like blue and blue are both segmented by this particular attention head. So there's like 12 different attention heads, and each of them gets a different color. And then we basically just like plot them all down on the same axis and look to see where each head is paying attention. So you can see like lighthouse, it's actually representing as two different words. Again, it's the same green attention head paying attention to lighthouse in both cases. Girl, the pink attention head is paying attention to girl and girls here. So we're really interested in actually now using these models to do unsupervised word segmentation, and then seeing if we can actually do like NLP tasks on these representations of the speech. So for example, we're looking into things like actually doing like syntactic parsing on these like tokens that correlate with word identity. And we also want to look at doing like automatic lexicon induction by tying these things down into like fine-grained units, such as like the Hubert tokens, like learned by the k-means clustering there, which have been shown by the authors to correlate with subword units like phones. So it'd be really cool then if we could like also learn to spell these words in terms of discovered units. And then the other thing that is really, really cool that we're starting to work on is going beyond just sort of like multimodal grounding on passive data and trying to see what we can do when we learn from other forms of grounded communication, such as interaction, dialogue, gesture, and all of that fun stuff. So if you'd like to read more about our work, you can visit the Salt Lab website at saltlab.cs.utexas.edu. And also, I just want to thank you very much for coming to my talk today and all of your attention and your great questions. And if we have time and people are interested, I can actually pull up the live demo on my computer and you can all come play with it. I hope it works in here. It's a little bit echoey, but I think it should. So thank you. And I'm happy to take questions now as well. This one? Yeah. Yeah, so I think what's going on here is, so we only have 12 different attention heads. So we only have like 12 different colors that we can kind of plot here, and there's almost like only 12 different like mechanisms that are available to segment things. So one of the things that we've been finding is that like certain heads will like pay attention to like several different words in the same sentence, but they tend to actually have some kind of like underlying semantic relationship. So for example, like blue and red together are detected by the same attention head. Yeah. Yep.
In the second work, you mentioned how it composed values that are really further joint representation that for certain, like it's almost sound symbols in there, certain subword components.
So we actually haven't looked at that. It's an interesting question. I am not very, very well versed. I'm a speech engineer, so my knowledge of morphology is not as good as I wish it was. So I don't know. So maybe you're referring to like the phenomenon that like front vowels tend to refer to like small, sharp, pointy things, and back vowels tend to refer to like large, smooth things, and whether that's something that's learned by the model.
Yeah.
I don't know. We haven't really looked into that. Yeah.
Also, more of what's
the code book? You mean like here?
Yeah.
So we actually just randomly initialize the code book with like 1,000 different entries. And it's just via like the learning procedure that those entries tend to like kind of gravitationally pull themselves towards, towards like clusters of frames that tend to like share the same underlying phonetic identity. And yeah, that's coming from the fact that so the idea is within like a mini batch of data, you can keep track of like every single frame and what it was assigned to. And then you can take like all the frames that were assigned to E1 and you can just like compute their empirical mean. And then you can push E1 a little bit towards that mean. And if you do that each training step, then that's basically how you're able to learn what these codebook vectors should be. Yep.
Am I audible?
Oh. Yes. So actually, I realize I'm sorry for those of you on Zoom. I should have been repeating all of the questions as they were asked. The previous question was about how do we learn the codebook entries here. The question before that pertains to why are we seeing like in this segmentation mask here, why are we seeing like red and blue being attended to by the same attention head? And the question that was just asked now is about the format of the audio, asking whether it was 16 kilohertz mono. And yes, so I think I recorded the speech initially maybe at 44.1, but all of the modeling that we did has just downsampled it to 16K. Yeah, so it's just standard wideband, speech. So the question is, have we done an ablation study looking at the number of different heads? Maybe. I actually don't know. This paper is actually, it's going to interspeech. And so I'm finishing writing it up right now with my student for a Monday deadline. And I want to say that buried within our Google Doc, there is probably some ablation studies somewhere, but we probably have to go dig them up. Most of the experiments we did, I think we looked at like 6 or 12 heads. Let's see, there's some more questions on Zoom, I think. Can we ask questions from Zoom? I have a 3-part question. Yeah, go ahead, Karthik.
But really very interesting work, David. Thanks a lot for connecting speech and vision very well. So yeah, I think this is expediting multimodal dialogue. So currently interested, so we're knowing about, is there anyone extending this for multimodal SLU and how are they doing it? Could you point to any work that's ongoing related to that? That's one question. The second question is, you mentioned about super benchmark Yeah, that's really great that you're trying to get your performance on the various subtasks. But are you also working on an open source benchmark for allowing models to learn in the vision plus audio perspective and create an open source benchmark for vision plus audio SSL models? So is there a open source benchmark work that's ongoing related to that? Yeah, these are my questions.
So as far as the benchmark, we don't currently have like a leaderboard or anything out there for, like the kinds of cross-modal tasks that we've been looking at. The data is all, it's all open source, and we've made it publicly available, as well as most of our modeling code. So there, it is possible to replicate, all of our results in that respect and improve upon our numbers. But formulating a more formal benchmark is something that we've thought about doing, and we'd like to do it. We just haven't really done it yet. And the first question, the current on multimodal SLU, the most recent work that what comes to mind is recently, so Meta has been looking at doing, this is again from the same team that developed like Hubert and Wave2Vec 2.0, is looking at simultaneous lip reading and speech recognition. So basically building these self-supervised models that have access to like visual data coming from a speaker's facial and lip movements, as well as the speech data that accompanies it. And they've actually done a really cool set of experiments on like audiovisual ASR as well as lip reading, showing that they're getting great results there. When it comes to doing multimodal language understanding, there is another group they're at Google. They're actually Jason Baldridge's group at Google Austin, working with Peter Anderson, who have recently collected a new data set called, so their initial, this is for the vision and language navigation task. Their initial data set was the room-to-room data set, and then they collected the room across room data set. And what's different about room across room is that instead of having like text instructions provided by the navigators, they actually collected the data by having people go along in this Matterport 3D simulator and talk about where the robot should move. And what's cool is you actually have a alignment between like the camera pose and the words that were spoken. So you can actually like see exactly like what somebody was looking at when they spoke a specific instruction. And you can do that, you can use that information even if you're only looking at text-based models, because you can basically just align the text to the speech, and then you basically now have an alignment between camera pose and the words of the instruction. I think they also had done some work where they were actually trying to get the models to learn to follow the navigation instructions end to end, just using the speech and not actually transcribing it into text. I don't know if they ever released the audio data for that data set, though. They may not have for privacy reasons. I'm not exactly sure what the status is on that. But room across room is the data set that you want to look at for that task. So those are a couple efforts in that direction that I know of just off the top of my head.
Yeah, that's really useful pointers. Yeah, I could just capture a few of them because I wasn't able to convert your speech into text at the speed, but yeah, I captured a couple of them. I don't know if others are there in the room who have questions, but I have another one that I put in the chat. If you have time, you could address that. Yeah. Or I can figure out, yeah, if it's not clear on the chat. Yeah.
So you're asking about whether you can leverage screen context for screen-aware speech recognition and understanding.
Yeah. I specifically, this year's Alexa prize competition was about multimodal interactions with screen context. So we built bots for people to be able to interact with Alexa prize bots for helping them cook recipes. And then there's a lot of times when people refer to, hey, are you talking about the one on the left or the right? Or even they're talking about something on the screen which needs a rich visual understanding, like the examples that you gave. And so it's very disheartening that still Siri and these assistants cannot understand screen context. And it's very important to leverage that, like just to say that, could you just go to the next page, or what is happening in this page? So this could really remove the barrier for those who are not very techy to just use speech to use screen systems. Yeah.
Yeah, I think that's a really great idea. I imagine Zoom has an enormous amount of data that would be really useful for that.
Yeah,
I don't,
yeah, thanks to,
but they probably
thanks
do.
to COVID, I think everybody moved to Zoom. So yeah. Yeah, yeah. Yeah, thank you. Thanks a lot for your answers. Yeah, thank you.
Thank you. Are there any other questions? Or are we at the time?
I think it's time to stop.
Okay,
So thank you very much for wonderful stimulating talk.
thank you.
Okay, there's snacks back at the LTI, as usual,
I'm gonna stop the recording if that's okay.